All right, let's go over MusicGen. So MusicGen, or simple and controllable music generation, is it's a model made by Meta, and it's one of the music generation models that you've been seeing lately. This is just one of them. I think Google made one as well. There were a few that came out recently, but yeah, this is one of them, and I want to kind of go over it to kind of see how like the current state of music generation. It's pretty good. You should check out the demo. Yeah, they have a GitHub for it, so that's pretty nice, and they open sourced the models, so it's really awesome. You don't you don't really see that lately where people are open sourcing the models, so big fan of that. Anyways, let's go over the paper. So like I said, they tackle the goal of music generation, and they do so in a kind of language model. It's kind of a language model task where they are modeling discrete tokens like a language model. Yeah, but first, like what are the difficulties with audio? So like whenever you see audio, you usually see a waveform, something like this. And this is represented by a vector. So it'd be like which represents the value in time. So this will be like the amplitude, and I don't know, at this point it may be like 1, and then at this point it may be like -1 or something like that. And then you represent it using a very, very long vector. And it's obviously in a continuous space, audio and speech and music, any sort of audio. So this vector is a continuous vector. And it is going to be very, very long. Like if you listen to music, the sampling rate is something like 32,000 hertz, which means to get 1 second of audio, you have to have a vector of size 32,000, which is massive. And doing anything with a vector that big is very, very annoying. But that's just for a second. So if you want more than a second, then you multiply, this is their sampling rate. And if you want anything more than a second, then you multiply 32,000 by however long your audio is, and you get this massive vector. So what they do is they call this f sub s, which is equal to 32,000 hertz. And that's what they're going to try to model. One of the things they bring up is like usually whenever you are looking at speech, you usually sample that at like 16K hertz. But for music, humans are very good at finding, like whenever you're listening to music and you hear something that's kind of incorrect, even if it's very, very minor, humans are very good at detecting that. So the sampling rate has to be even higher. Yeah, and they bring that up right here. So you need a really, really high sampling rate. That's very difficult to model. So what they do is they use a model called Encodec, which my last video was on in Encodec. You should go check that out. But I'll go over it briefly, real quick. But I'm not going to go into more of the RVQ part. But I'm not going to go into it in too much detail. I suggest taking a look at the Encodec video because it's a very the model is a good basis for a lot of things, Encodec and RVQ. So what does Encodec do? So let's say we have a signal, this vector of size 32,000. So 32,000. We then throw this through multiple convolutions, and we kind of bring down. This is our encoder. So we kind of bring down the size of the audio and kind of extract the features out of it. Because doing anything with this raw signal is very it's not a good representation of the data. So we encode it to a smaller space. which they call f sub r. Because f sub s is equal to 32,000, and f sub r is like a smaller latent space, which I think is just 50 hertz. Yeah, they encode this to 50 hertz. Yeah, massive compression, so 32,000 to 50. Yeah. And just a reminder, this is for 1 second of audio. They don't go beyond that, and we'll get into why in a sec, or we'll get into how they kind of leverage that later. But this is just a second of audio that we're dealing with, so 32,000 part vector. So this is our encoder. It's just a convolutional neural network in 1 dimension. And then what you do is you apply RVQ. Sorry, it's 50 by the number of features, and I'm guessing they just flatten this out to be 50 by f sub r. So f sub r is just whatever this encoding dimension is, which is 50 by, what was it? I am losing my, whatever. 50 by the number of features. I think it was 64. So f sub r is equal to like 50 by 64 for 1 second of audio. So we have this vector that's much smaller. It's composed of the features of the audio as opposed to just the raw audio. Anyways, our CNN encoder brings out the features in the audio into a smaller representation that's easier to deal with, and then we apply residual vector quantization. And residual vector quantization, it transforms this vector from a continuous space to a discrete space. And remember, the goal of MusicGen is to model stuff using discrete tokens. So the first thing we have to do is take our audio, and then we have to put it in a discrete format. We can't just deal with it in continuous time, or in a continuous domain, as transformers are made for modeling discrete tokens whenever you're dealing with it autoregressively. It doesn't generate stuff continuously. It generates stuff 1 token at a time, which is discrete in time. So we need to have discrete tokens. RVQ discretizes our vector, and it does so by breaking it up into multiple vectors. So in this case, it would be like 4 vectors. And the way it does it is it does it by doing a sort of, it uses lookup tables, or code books, as they call it. So we have our vector, which is of shape f sub r, and we have a code book, which is of shape, it is n by f sub r. And what we do is we take our code book and we look. We see. So we look at our vector, our input vector x, and we look at all the vectors in our code book, and we see which one is the closest. So each of these is a vector. So this is vector 1, this is vector 2, 3, 4, 5, 6, n is equal to 7. In this case, our code book has 7 entries. And we take our input vector and we kind of do a lookup to see which vector is the closest in here in our code book to the given input vector. Let me give an example down here. So if our code book has say 5 entries, this is the example I gave in Encodec, by the way. 6 entries. 0, 1, 2, 3, 4, 5. So this is n is equal to 6. And say our f sub r is equal to 3. This is codebook 1. And let me just write out the 0, 1, 0, 0, 0, 1. The codebook entries are learned, by the way. 1, 1.5, 0, 0, 1.5, 1, 1, 1, 1. Yeah, I mean, these are just random, the entries I just put in there. But anyways, say our vector is 1, 2, 3. Makes it easy. So this is x, f sub r is equal to 3. This is x, our encoded vector representation of the audio in continuous space. And what we do is we look to see which vector is the closest in our codebook to the vector here, to our current vector. In this case, it would be vector 5. And what we do is we subtract, we take the residual between the two. In this case, the residual would be 1 minus 1, which is 0, 2 minus 1, which is 1, and 3 minus 1, which is 2. This is our residual, r, which I'll call r. So r is equal to that. And we can kind of store our entry over here. So we have 1, 1, 1. That's our entry. Now what we do is we take a second codebook, which I'm going to say also has 5 entries, or 6 entries. 0, 1, 2, 3, 4, and 5. And then f sub r is the same because we're matching in the same dimensionality. So 0, 2, 0, 0, 0, 2, 0, 0, 0, 2, 0, 1, 1.5, 1, 1, 0, 2, 4, 6. All right, and then our vector is, so instead of taking our input vector, we look at our residual vector, which is 0, 1, 2. Yeah, 0, 1, 2. And then what we do is we look again to see which value is closest to the residual. In this case, it would be 3. And then we take the residual of that. We take the difference between these two, so it'd be 0, 0, and 0.5. So now our residual is this. And now we have two vectors, 0, 1, 5, 0, 1, 1.5, which kind of represent our input vector. So if we sum these up, then we get a vector that is 1, 2, 2.5, which is, yeah, I mean, it's close enough to this vector representation. That's kind of the downside of residual vector quantization, but that's the thing. It's a quantizer. It puts things into discrete bucket. It clumps vectors together that are close enough in the latent space, and it puts them in the same so-called bucket. If we had a vector that was 0 or 1 to 2.5, then in our residual vector quantization, it is the same as 1 to 3, and we would get the same output. We would get the same output vectors, but yeah, that's how residual vector quantization works. And you do it so that you can bring a vector from a continuous space and put it into a discrete space. It also kind of you can also kind of compress it using indices. So in this case, the indices would be 5 and 3. So now we brought it from a continuous, or we brought it from a continuous space, which was this space, and then we brought it down to a two-dimensional space, two-dimensional discrete space. So that's kind of how residual vector quantization works. And let me find it in here. Yeah, that's how they describe it, or that's the main method that they use. And like I showed, you can reverse residual vector quantization with a little bit of loss because you're doing quantization. So if you reverse it, then you get your input vector, which is of shape f sub r, and then you throw this through a deconvolution, which would blow this vector back up to f sub s, our original signal, which would be 32,000. So yeah, it's Encodec is just a encoder, is just an autoencoder pretty much. It's just an autoencoder with residual vector quantization in the latent space. But the reason we do this is that we can get our encoded discrete representation. So what this looks like is we have a vector of shape 32,000. We throw this through our encoder block, and then we get out, this would be f sub r, or f sub s, and then we get out f sub r, a vector that is slightly smaller, and then you throw this through, in this case, they use 4 codebooks. So codebook 1, which will output a vector of shape f sub r, and then you take the residual, codebook 2, you take the residual, r, you throw that through codebook 2, and then you get out another vector, which is f sub r again, and then you do this a third time, codebook 3, you get out another vector, and then you do this a fourth time using the residual again, and you get out a vector of shape f sub r again. So now we have this vector that can be represented by that's kind of in a way tokenized, and it's tokenized along this dimension here. So if we group these together, then you get a output from our residual vector quantization that is of shape f sub r by 4. K is equal to 4. K, the number of codebooks, is equal to 4. There we go. So this is our, draw it like this. So this is our input into the transformer, which we're going to model. And this will be one token. So it's not, a token isn't along the codebook. A token is one part of the encoded representation of all codebooks. Which is what they have a bunch of methods for combining these together. You don't just stack them like I did here, and we'll get into why in a little bit. But you can kind of visualize it like this for now. So now we have an encoded representation of our audio. That's easy to deal with. It's easy to deal with this. It's easy to deal with something that is a set size and it's a matrix. It's not a really long vector. It's easy to deal with. We just throw a transformer at it, and that's exactly what they do. So we have this encoded representation of our audio, and the goal is to take our token representation, where tokens are 1, 2, 3, all the way to f sub r, and then put this through a transformer, or I guess 1, 2, 3, s, and then have it predict which it will output tokens, and normal autoregressive training strategy. It'll output tokens, and then we use this to predict the next token in the sequence. And since the encoded representation is inherently time-based because of the convolutional neural network, you predicting this token would be like predicting the first token in the time sequence, and then predicting this token would be like the next token in the music encoded sequence, and then predicting this token would be like the next token in the music sequence. So it's inherently time-based, where time flows to the right, just like speed, or just like text generation. So you can think of generating the way they want to generate audio is by generating one token at a time in this discrete space, just like you would with text, except this is in the latent space of the autoencoder. So we can't really visualize what this would represent, but yeah, you're basically generating it one codebook entry at a time. And remember, our codebook looked like this. So you basically are generating, this would be your first token, and this would be your second token, and then this would be your third token, and so on. And you want to do this autoregressively. And they do this so that you can generate 32,000 a 32,000 hertz audio clip. But since this is in the latent space, you don't have to do 32,000 tokens. You only have to do, I think it was 50 tokens, 50 by 64 tokens. That's what they had above, to generate this sequence, which is very nice. 32,000 tokens would take forever to do auto-regressively. 50 tokens does not. 50 by 64. So this is a very nice property. And that's their goal. You encode this, and then you do an autoregressive generation on the discrete token sequence in the latent space. One of the problems with this is, like I said before, you can't just stack the tokens. So we have our sequence, which is broken up. This is our k is equal to 1. This is our first bucket. This is our first vector in the. This is our first vector from codebook 1. This is our second vector, trying to model the residual, and then we have a third vector, and then we have a fourth vector because we're using 4 codebooks. So you get 4 vector output. And what you could do is you could just stack them. So now we have a rectangular matrix, and you just stack them together. You just squash them together. But that's a very naive approach. The problem with that is there's compounding error. So say we generate this first token here. We generate this first token here, and let's say it has a little bit of error. Then whenever we generate this token, all it knows is I need to generate it's different than modeling text. If I were to generate if I generate a token that's based off the previous token, then and the previous token had a little bit of error, then the next token is going to say, okay, I know that based off this first token, which has a little bit of error, but I don't know it has a little bit of error, it models the error as well. So the second token models the error of the first token, and if the second token has a little bit of an error, so it's not a perfect generation, then the third token will model the error of the first token, or the first token and the second token. So the third token now has even more error because the first and second token had a little bit of error, because the generation isn't going to be perfect. Since you're using a neural network, the generation is going to be almost perfect, but it's not going to be completely perfect. So the error is compounding due to this. And the problem is this first codebook is very, very important. The reason the first codebook is very important is because it directly models it's the first stab at modeling the input vector. The second vector only models the residual. So the second codebook is more important than the third and fourth codebooks, but it's not nearly as important as the first one, which models everything, or which takes the first stab at modeling the input vector. And the codebook that takes the first stab at modeling the input vector is going to model the most of the input vector. So this first codebook needs a lot of weight compared to the other codebooks. So what they do is they say, well, how about we stagger it? So instead of modeling it where we just stack it, we can kind of stagger it a little bit, like this, which is represented in the rest of the diagrams. Actually, not in the volley pattern. So in this case, you stagger it a little bit, so kind of like a staircase where, like that. And then this is just the 0 or some special token or whatnot. A special token indicating empty positions in the pattern. And in the normal case, since this part, let me get out blue. There. So in the normal case, this vector would be generated at once, meaning the first time step is generated at once. But in this case, this first token is generated, and then the second token, or the second token, you can kind of think of it as fixing, like whenever we're doing codebook generation, this first entry takes the first stab at generating X, or generating our encoded audio representation. And then the second part, so this would be codebook 2. This would be codebook 1, codebook 3, codebook 4. Sorry, I kind of flipped it here. But yeah, this first token that's generated would be the first entry in codebook 1, and it would be no other entries in any other codebook. Those are just thrown away. And it predicts the first entry in codebook 1 by itself. It doesn't have anything else to represent. And then the second entry predicts the first entry in codebook 2, and you can kind of think of it as correcting what was generated here. Because remember, codebook 2 models the residual between the generated out, or the audio we want to generate, and the audio that was modeled by codebook 1. So codebook 2 is just modeling the residual. But if you generate them all at the same time, then it's really difficult for it to know what to model because the residual doesn't exist yet. It's just, since transformers model, like the transformer itself is continuous, but the output is discrete, then there is no error. There isn't really any error, so it won't model the residual correctly. But if you have it in the second token, then it's able to fix what codebook 1 didn't have to generate the first part of the audio clip. I hope that makes sense. But yeah, so then codebook 1, codebook 1 we could generate a part of codebook 1, and then we generate a part of codebook 2, still representing token 1. You can kind of see that here, here. So this token right here would model is codebook 1. So codebook 1 we generate the first part of codebook 1, and then we generate the first part of codebook 2, and then we generate the first part of codebook 3, and then we generate the first part of codebook 4. So now we have a single token in our input in our encoder representation of the audio. So this first token is generated. This fixes this kind of models the error of that token. This models the error of that token, and this models the error of that token, or of that part of the token. And if you do it this way, then the first 4 steps just model the first token, and the next 4 steps just model the second token in the sequence, and so on. But it's very long. The problem is this is very, very long, and since we're dealing with audio, we already have a hard enough time. And like I said, the parallel pattern, since these tokens are they're discrete. They're modeling a discrete output. But in the transformer, it's in a continuous space, and it doesn't know, like this second token doesn't know what the error of the first, the second codebook generate the generated output of the second codebook doesn't know the error of the first codebook. Then this modeling strategy isn't going to do very well, and then the error compounds and so on, and it doesn't do very well. The whole point of the codebooks is so they can fix each other. So this one doesn't do very well. The volley pattern is thinking, well, the first codebook is the most important, right? And if the first codebook is most important, then why don't we just generate the entry of the first codebook by itself, or we generate every entry of the first codebook independently, but since it's slow to do this strategy up here, then why don't we just generate the rest of the errors, the other codebook entries together. So you model the most important codebook independently, and then you model the other codebooks together. And the authors are like, well, maybe we can do a little bit better. And in this case, this is what they find that this works really well, where it's both compact, so it doesn't take forever to generate, but it also isn't stacked, so the errors can actually model each other. So you can think of this token 1, it just generates the first entry of codebook 1, which is the first stab at generating the actual output, and then there's a little bit of error after this token. So then you go to token 2, and token 2 The second entry is like, okay, I'm going to model the error in the first token, but I'm also going to generate the first stab at token 2 in our output. And then the third token would generate would do the same, where it models the error of token 1 and token 2, but it also generates the first part of token 3, and so on. And in this way, it's able to model the error, but it's also able to do it quickly. So you don't have to take 4 times as long to generate a sequence. It's just the number of generations plus 3. Maybe they cut it off, but it would be the number of generations plus 3 if you're modeling all tokens. Maybe they cut off this part up here. Yeah, but yeah, those are the token generation strategies, and yeah, I mean that's there's other strategies you could do, but these are the ones that they kind of look at. But yeah, I mean that's basically all there is to it. You have an audio clip, or you have an audio clip. You have an audio clip which is of 32,000 hertz. You throw it through a convolutional encoder, CNN encoder. You get out a which is f sub s. This is f sub r. It's a smaller latent vector. You do residual vector quantization, so you get out your 4 long sequences. This is residual vector quantization, and you do this for all audio clips, and all audio clips that you're training on. And then whenever you're doing generation, or then you model the transformer. And the way you model the transformer is like a normal autoregressive transformer. And this will output, so actually it's not like that, sorry, I drew it wrong. It's like this, where it's broken up, and each of those go into the transformer. Yeah, right, so each of those outputs its own vector, like this, using the strategies over here, and then this part goes through our decoder, like this decoder, and then that should be smaller, like this. And then we get out our x hat, which is our prediction, which is in f sub r. Right, yeah. No. You need to do residual vector quantization again. So you get out your 4 vectors, and then you concatenate these, and you do your residual vector quantization, your reverse residual vector quantization, and then you get out your predicted latent vector, and then you throw that through the decoder. And then you get out your x hat, which is the prediction, f sub r and f sub s. So you take your input audio, you throw it through the convolutional encoder, you get out some latents, you then quantize those into 4 buckets, 1, 2, 3, and 4, and you model that using a transformer. And then you train on this part right here. You train on this part. But then during generation, you will model this part right here. And the way you train it is you do it just like a normal. You can kind of think of the code books as a vocabulary. Notice how the code books have a certain size to it, a certain size n. So whenever we're doing a generation, you'll give it, say, the first few tokens, the first 2 tokens. And remember, these tokens are in some latent space, and then you get out size 4, because there's 4 codebooks. And you take the last token, and you project this into n times f sub r. Yeah, you model this as n times f sub r. You take this token and you take the last token and you project it to a space that is n times f sub r. And you can think of this as predicting as a softmax over every entry in the codebook. So remember, each codebook has n entries. So this would be n entries for each codebook: codebook 1, codebook 2, codebook 3, codebook 4. And this is a softmax over, like this would be a softmax, and this would be a softmax, this would be a softmax, this would be a softmax, because we're predicting, if we're doing, say, this as an example, then the softmax, say we're doing 3, because this would be 1, 2, and 3. Then codebook 1 would want to generate this token right here, token 3. So this would be T3 sub 1, because it would be T3, be T2, this would be T1, and this would just be 0. So that's what it's doing the softmax over. You take this token and then you project it. So you project each of the parts of that encoded token to to the output space, and then you can sample each of these softmax distributions to get your next token. So this would give you some index. This would be index 1, or yeah, this would be index 1, index 2, index 3, index 4 for each of the codebook entries. And then just like your normal autoregressive decoding strategy, you would then throw that through, project this into the output, or project this to an output distribution, and then you model that token again until you get out however many tokens you want to generate the 1 second of audio. And that's their strategy for doing this. All they're doing is they're taking they're taking the music, they're projecting it, they're doing residual vector quantization, and then they model that with a transformer and a decoder. And this is our model right here. So take a transformer, you do an autoregressive decoding strategy, and you can reverse residual vector quantization that. You throw it through the Encodec decoder, which you train because it's an autoencoder, so you have this decoder. And then this will be 1 second of output music. And this 1 second of output music will be, it's just 1 second. But what you can do is you can kind of take a slice of this 1 second. So you can say, well, I want the last, say, 1/4 of a second. And then you use that as well context into the transformer again. And instead of just modeling it where it has no context, you can model it where it uses 1 second of context of the output audio, or the generated audio. And you can kind of continue the music on for a long sequence of time. Just like with text. Like with text, you can't throw an infinite length of text through a transformer, but you can take the last segment of it, or a summary of the other text, and then throw that through the transformer, and it can model the rest of the text. But yeah, that is that's pretty much the whole basis of the MusicGen model. Let's see some of the results compared to the other models currently being used. It's pretty. It looks to do better, but it looks to do better by pretty significant numbers. And one thing that they did find interestingly was going like the audio or the music generation. It did really well, or it did really well at 1.5, but it did even better at 3.3 billion. It did really well at 3.3 billion, but as they went higher than 3.3 billion, it did really well up until 1.5 billion, but once they got to the 3.3 billion model, it wouldn't do better with the music generation, but it would do better at kind of being guided by the prompt. And you can guide the transformer just with normal text guidance with a cross query, but it would follow the prompt better, which is kind of interesting that the music wasn't inherently better. It was just better at following a prompt as you scaled it. So that was an interesting thing. But yeah, it's interesting that it does a lot better than like MusicLM, which is another recent noise generation or music generation model. The results do look pretty good, and if you listen to it, they are pretty good. So I highly suggest taking a look at the results in their GitHub repo or just playing around with it. They also look at the different decoding strategies or different like token interleaving strategies because of the 4 codebooks, and they find that flattening works the best. Flattening was where you had the 4-part generation, so that would be the first token and then the second token, and obviously that would do the best. But obviously that one is really freaking long too. It's really long. Nobody wants to deal with that. The generation is 4 times longer than every other generation, so that's not fun. But the delay strategy where you did that would be the first token right here, and then the second token would be underneath it, and then the third token, and so on. They find that works very, very similarly to the flattening strategy, but in a fourth of the time. So, which is way better. Or no matter how good it is, this will take forever to generate. But they also find that it does better than the other decoding strategies like volley. And if you remember the volley one, that was the first tokens, and then it would generate the first codebook, and then it would generate the other 3 codebooks in parallel after that, and it did better than that. But it's also it takes half the time to generate, or half the tokens to generate, which is very nice. So delay strategy, token strategy matters a lot. That's what take away from this this chart. But it also the delay strategy does pretty well. So very, very interesting results they had here. Yeah. One other thing is they use this thing called datum, and I don't know what it is, but it looks interesting. And they find that on smaller models, yeah, they had datum 300 million parameters. Yeah, so on smaller models, it looked to do better, but then on larger models, it did worse. So I don't know what datum is, but if it's a new optimizer, then this may be interesting to kind of take a look at for small scale. But anyways, yeah, that was MusicGen, simple and controllable music generation.